Swayam Prabha. Digital India. Educated India.
Good morning. Last lecture we looked at how to use a different method, what we called as the displacement method, to solve or analyze a statically indeterminate structure. Now I am not going to use the word statically indeterminate anymore, because if you look at the displacement method, there is no computation of static indeterminacy in the entire procedure. In fact, I will show you later that even a statically determinate structure can be solved using the displacement method. The only point that the displacement method concentrates on is actually the kinematic indeterminacy, or the number of degrees of freedom in a structure, because the displacements corresponding to these degrees of freedom are what we first find out, based on which we complete the analysis of the structure. So now today I am going to continue looking at how to use the displacement method. Last time I introduced you to the slope deflection equations, and we saw how you could use the slope deflection equations to solve a particular problem. Remember that what we did was that we had a problem in which we had a single degree of freedom, and we actually wrote down an equilibrium equation corresponding to the degree of freedom, and that equilibrium equation actually enabled us to solve for the unknown displacement corresponding to that degree of freedom, based on which we could find out the bending moment diagram for that. Now the slope deflection equations, the way I have written them, are not complete. I will explain what I mean by that. Let us look at a particular problem. Let us look at this problem. So I have a loading here, let us say P, okay, and I want to know what my M A B, what my M B A are. Now if you look at this particular case, you will agree that given this load, M A B and M B A are going to exist. They cannot be equal to 0. Do you agree to that? Okay. So now, but let us look at the slope deflection equations. What do the slope deflection equations say? M A B is equal to 4 EI by L theta A B plus 2 EI by L theta B A minus 6 EI by L squared delta B A, and M B A is equal to 2 EI by L theta B plus 4 EI by L theta BA minus 6 EI upon L squared delta BA. These are the equations, okay? Now, if I look at the slope deflection equations, what is theta AB? What is the rotation at this point? Since it's fixed end, this is equal to 0. What is theta BA? Since this is a fixed end, this will be equal to 0. What is the relative movement of this point to this point? These points cannot move vertically, so this is equal to 0. So then what is MAB equal to? According to this equation, MAB is equal to 0. Similarly, you will see that MBA is equal to 0. But this is wrong. Why? Because we can just see that there has to be an MAB and MBA. They cannot be equal to 0. So therefore, the slope deflection equations, that the way we wrote them, are okay as long as you do not have a load on the member. When you have loads only on the joints, these kind of equations are okay, because remember last time when I solved, where did I apply the load? The load was a moment applied at the center support, which was at the joint. It was not on a member. But this kind of load is on a member, and when you have a member load, so this is not valid when you have loading on member. Not valid. So what do we do? How do we solve this problem? Obviously, slope deflection equations still have to be used because they are the fundamental equations in displacement method. Okay. So how do we solve this problem? Well, let us look at it. And therefore, let us look at the problem that I have defined. And that is, let's look at this. Let's try to solve this problem. In other words, the slope deflection equations as we wrote them are incomplete, and I will show you how incomplete they are. Okay. Let's look at this. This case, there will exist an MAB and there will exist an MBA. Now, how do I find out this MAB and MBA? Okay. What are these moments? These are actually the moments at the fixed ends. So I'll call them as fixed end moment AB and fixed end moment BA. Okay. So these are the moments at the fixed end. And if we somehow are able to compute these, okay, and if we add these to the expressions for slope deflection equations, then maybe we'll have something. So let us try to find out how we can get this FEM-AB. Now, if you look at normal books, you will see that people actually, at the back of the book, you will always see that given various kinds of loads, okay, they will give you expressions for these fixed end moments. So therefore, for example, let me just tell you that if you look at any book, structural analysis book, and you say that you have a load, okay, at the center, let's say L by 2, L by 2, then they will tell you, these are given in handbooks, this fixed end moment is going to be equal to PL squared by 8, and this is also PL squared by 8, but in the opposite direction, it will be in this direction. If you note, fixed end moment is what? Force into this thing, displacement. So it's not L squared, it's PL upon 8. Okay. Now, the point is, you will always see that I will never be able to tell you the formula because I really don't try to remember formulae. And again, as I have said all along, that the entire focus of this particular course, as I teach it, structural analysis, is not to give you a whole set of formulae that you are going to have to remember to be able to solve. Okay? For example, I give you the slope deflection equations, and then I explain to you how to how to actually obtain the slope deflection equations from first principles. Okay? And as far as the fixed end moments are concerned, I'm going to do exactly the same thing. I am going to tell you how to compute the fixed end moments given a load, so that you never have to remember a whole bunch of formulae. Of course, if you're just doing an analysis, it always helps. But when you're actually learning a course, learning a whole lot of formulae does not, I think, in my opinion, help you in understanding how to solve problems. Okay? So therefore, I am going to again go back and explain to you how to compute the fixed end moments, so that given any loading, which is, you might have a loading which may not be there in any handbook. Okay? How will you get the fixed end moments? I'm going to spend the whole day of today explaining to you how to obtain fixed end moments, and then I will show you how to apply this entire procedure for a given structure. Okay? So let us look at this. Let us look at this situation. I'm going to go back to the original, that I have a uniform beam, so its length is L, and EI is the flexural rigidity at any cross section. Okay? So it's a uniform beam. And this beam, let us look at a particular example. I'm using only as an example. Okay? You will see that my procedure can be used for anything. And this load is applied at the midspan. Okay? And our entire goal over here is to find out the fixed end moment at A and the fixed end moment at B. How will we solve this procedure? Okay, how will we get these? The procedure is very simple. I always go principle of superposition. So I'm going to say that, look, I'm going to take this structure. Okay? So I'm going to say that this structure is equal to this plus see, what I have done over here is I have taken this structure, which is a fixed beam. I have made it into a simply supported beam, and I have said that in a simply supported beam, you know that the bending moment here and the bending moment over here are 0. Okay? So what I have taken is that, look, this structure, I have made these fixed end moments as external loads. And I have said that, look, this entire thing is equal to this plus this. But that's not good enough, okay, because we know this, we don't know these, we have to find these. What else has to be satisfied? Note that under this load, what's going to happen? This is going to become something like, this, the rotation. I'm just drawing the rotation for this. The rotation will be, the deflection pattern will be something like this. What will be the deflection pattern for this? Something like this. What do the deflection patterns have to satisfy? Note that one difference between this plus this is the fact that not only as the loading has to be taken, but note that the displacement here and the displacements here are 0. The displacement here and here are 0 because, axial rigidity, so this point is not going to go. So displacements are 0 at this point. What additional thing is 0 over here which is not 0 here? The rotations. So therefore, what we have to say is that we're going to compute theta AB under the loading. Okay. Note that the way I have shown it, it's negative, because my positive is always anti-clockwise. And this is theta BA 0. Now, what we are going to do is get these theta BA under the moments, and one additional factor that this has to satisfy is that theta AB 0 plus theta AB due to the fixed end moment is equal to 0. Theta BA 0 plus theta BA due to the moment is equal to 0. So, therefore, you see you have this compatibility that you have to satisfy, that the moment at this point is equal to 0. Okay. So, you see what I am trying to find out? I am trying to actually find out the fixed end moment using the force method. Okay. It is very interesting that I am using the force method to solve, because if you look at this, how many redundant forces do you have in this particular case? These two. So, since you have these two as the redundant forces, I am actually writing down equations, compatibility equations corresponding to this. So, I am to find out the fixed end moments, which I am going to use in the displacement method. Okay, I am actually using the force method to compute these fixed end moments. Okay. So, let me just go through these steps for this particular one, so that I can explain to you how to do this for a general type of loading. Okay. So, let us see what is the rotation. So, therefore, the goal here first is under the loading to find out the rotations at the two ends. So, let us apply the load. How do I find out the rotations? Well, find out the rotation. Under this load, what would be the bending moment diagram which will look like? Again, I am not going to spend time telling you how to compute bending moment diagram. By now, you should know this. It is going to be this way, and this bending moment is this way. Okay? This is the bending moment. I leave it up to you how to obtain it. You should, by now, for a statically determinate structure, you should be able to draw bending moment diagram, shear force diagram, and any other diagrams that you have to draw. Okay. So this is my bending moment diagram. Okay. And since EI is a constant, this M upon EI diagram is going to be equal to PL upon 4EI. Simple. Okay. Now, I want to find the rotation here. What would I do? Well, principle of virtual force, right? Apply a unit force here. If I apply a unit force here, what's the bending moment diagram? Unity. And for finding out this bending moment over here, what do I need to do? Well, let me first do this. Okay. So, this is the bending moment. So, what would theta AB equal to? 1 into theta AB is equal to the internal virtual work, which is M upon EI dx, which I am going to do area under these two curves. Note that I have to take two curves actually. Okay. Although explicitly you will see that you will say that, oh, I can take this entire thing and find out the area under this curve and draw its centroid. Okay, I know where the centroid is. But note that these integrals are always valid only where, so in this particular case, actually this integral, since this expression from here to here is different from the expression from here to here, actually you have to take two integrals. And for each integral, you need to find out its area under the curve. And so, therefore, this one is going to be equal to PL upon 4EI. Length is L by 2. So, L by 2 by 2. So, that's L by 4. So, this is the area under this curve. Okay. And where is its neutral axis, you will see that, it's centroid, it will be at 1/3 from here, 2/3 from here. So 2/3 of L by 2 is, L by 3. So that means at L by 3, what is the corresponding value? You will see that it will be equal to 2 by 3. Note the fact that this is sagging and this is hogging, so it's actually minus because the sum total is minus. Similarly, if I take this side, you're going to have, so this is one part, then let me add the next part. The next part again will be PL upon 4 EI multiplied by L by 4, and this is acting at this point, which is 1 by 3. So if you look at the 1 by 3, it's going to be 1 by 3. So if you add the two of them up, you will see that this will be equal to minus, so therefore theta AB due to the loading is equal to minus PL squared upon 16 EI. Let's look at the consistency of units. P is in terms of Newton L squared, so it's Newton meter squared. What are the units of E? E is Newton per meter squared. I is meter fourth. So if you Newton per meter squared into meter fourth is Newton meter squared. This is Newton meter squared divided by Newton meter squared. It's dimensionless. And what's the units of theta? You will see that it's in radians, which is dimensionless. Okay, so this is consistent. So this is my theta AB 0. Let us find out theta BA under the same loading. So under the same loading, this is acting at L by 2, same M by EI diagram. I'm just drawing it all over again, just so that for EI, this is my M by EI diagram. And now I want to find out, this is A, this is B, this is C, A, C, B. And now I want to find out theta BA. So theta BA, what do? I apply a unit force corresponding to the theta, which is a unit moment, and then find out the bending moment diagram. And the bending moment diagram over here is going to be 1. So this is my small m diagram, and therefore 1 into theta BA 0, that's the external virtual work. Okay, theta BA 0 is going to be equal to the area under this curve, and I'm not going to go through, I've already gone through the steps for the last time. I'm just going to write down L by 4. So if I take this, it's going to be 1 by 3. And note that both of them are plus, so this is going to be plus because both of them are the same sign. Plus PL upon 4 EI into L by 4, that is this part is going to be 2 by 3, and therefore theta BA 0 is going to be plus PL squared upon 16 EI. What does that mean? That under this loading, the displacement pattern is this way. Note that this one is equal to PL squared upon 16 EI. This one is equal to PL squared upon 16 EI. Note that this is minus, which means clockwise. This is plus, which means anti-clockwise. Everything works out perfectly. And since the loading is symmetrical, even the displacement pattern will be symmetrical. Okay, so we have found out theta AB and theta BA 0. Now we need to find out what are going to be theta AB and theta BA due to the fixed end moments. So in other words, I am going to put M1, let me just put M1 and M2. Okay? M1 and M2. So if I plug that in, what do I get? Let me apply them separately, because anyway I can do superposition. So I'm going to take this plus this. Is that okay? It's the same thing, right? Two loads acting, I'm just considering them as two separate loads. Okay? So I can find out the theta AB due to this moment, find out the theta AB due to this, and sum up them up. Okay. Under this loading, what kind of moment diagram do I have? I have M, and this one is going to be this way. Okay. And it's linear. Okay. My things look really bad. And how do I find out theta AB? Apply a unit moment here, and for finding out theta BA, apply a unit moment here. For this, the bending moment diagram is this way, 1 into, and for this, it's, for this, the bending moment diagram is M2. Okay, so I have drawn all the bending moment diagrams. Why? Because these are the real loads, so I'll finding out, this gives me the curvature diagram, and these are the virtual moments. So I'm going to find out due to this and add, and due to this and add it. Okay, so if you look at it, theta AB M, due to this is what? Area under this curve, and then the value of this at its centroid. So what's the area under this curve? M1 upon EI multiplied by L by 2, and it's at 2/3 the distance from this point, so that value is going to be 2/3. Okay, so if you look at this and look, both of them are hugging, so this is plus. So this is the moment due to this load, sorry, the theta AB at this point due to this load. Now I'm going to add the theta AB at this point due to this load. So for that, this is the real curvature and this is the virtual. So if you look at this, what is the area under this curve? It's going to be equal to M2 upon EI multiplied by L by 2 multiplied by, look, this is sagging, this is hogging. So it's going to be minus, at 2/3 you will see that at the CG, the M1 value is equal to 1, minus 1/3. So this is my theta AB. Similarly, theta BA, for theta BA, this is the virtual and these are the two reals. So for this one, the area under this curve, M1 upon EI into L upon 2 multiplied by, at this point you will see, and this is sagging, this is hogging, so it's minus 1/3 plus M2 upon EI, that is due to this loading, where this is the real curvature and the area under the curvature diagram is going to be this, and since these are both sagging, this is going to be plus 2/3. So if I put these down, I'm going to just put all of them together and you will see that I get Now note that what's the big deal about this? I already know this, don't I? I already know this. Remember, we computed it last time, L upon 3i, L upon 6ci, L upon 6ci. I've already done this. I use this to obtain the slope deflection equation. So I've done this already and I've got the same thing. Okay. Now, the only point here to note is, and what is theta AB 0? Let me write that down. Theta AB 0, I've already computed it, is equal to PL squared upon 16 EI, and theta BA 0 is equal to PL squared upon 16 EI. The only thing is that if M1 and M2 are the fixed end moments, then theta AB 0 plus theta M. So now I need to find out those fixed end moments, right? So what I'm going to do is I'm going to put this plus this equal to 0. Okay, and therefore you will see that ultimately, if I say that I'm not going to explicitly put them equal to 0, I'm going to show you what we are going to be doing. So what we're going to say is that, look, this implies that due to the fixed end moments, this is equal to minus AB. In fact, this is what I'm going to do. I'm going to say that theta AB or BA, I'm just writing down, is equal to minus of theta AB due to loading. Okay? Once I say that, and I substitute that in, what do I get? I get that for fixed end moments, and I'm going to put down fixed end moment AB L upon 3EI minus fixed end moment BA L upon 6EI is equal to minus theta AB 0, because theta ABM is equal to minus, and so fixed end moment at AB L upon 6EI plus fixed end moment BA upon 3EI is equal to minus theta BA. This is by definition, okay, because this plus this is equal to 0 for fixed end moments. Okay. Now, okay, if I rewrite this, look at what comes up. This basically becomes L upon 3EI minus L upon 6EI minus L upon 6EI L upon 3EI into fixed end moment BA is equal to minus of theta AB 0 minus theta BA 0, minus of theta AB and theta BA 0. So can I find out the fixed end moment? Sure, take inverse of this, but note what the inverse is. Okay, you've already done this, so you will see that fixed end moment AB and fixed end moment at BA is going to be equal to what? You will see that it's going to be equal to 4EI by L. We've already done this. When did we use this? To develop the slope deflection equations. Okay? So if you look at this, this becomes equal to minus here, because it's minus theta AB 0, theta BA 0. And if you look at this, this is equal to fixed end moment AB is equal to 4 EI by L minus theta AB0 plus 2 EI upon L minus theta AB0, and similarly fixed end moment at BA is equal to 2 EI by L theta AB0 plus 4 EI by L theta BA0. So once I have described this, doesn't this remind you of something? This is actually the Stokes deflection equations that we've already developed last time. Okay, and so therefore the only thing that you do is to find out the fixed end moments, you just compute the theta AB and theta BA due to the loading and take the negative of that, substitute that in the Stokes deflection equations and gives you the fixed end moment. Okay, so now if I do that, let us see for this particular case what we've got for this case. P at L by 2. What is the fixed end moment? The fixed end moments, what were theta AB 0, theta BA 0, we've already computed this, PL squared upon 16 EI. Okay, so I'm going to plug those in to my Stokes deflection equations, and what do I get? Fixed end moment at AB is equal to, let's see, by the way, sorry, let's go back. Let me just, whenever I rush, I get into trouble. Theta AB was negative. Let's go back. Theta AB was negative of PL squared upon 16 EI, and theta BA was plus PL, so let's put that in, please. So if we go back there, we actually see that theta AB is minus of theta BA, which is minus. Okay, those are the values. So I'm going to plug in the values of the fixed end moment into the, so I'll have 4 EI upon L. That's the Stokes deflection equations. Negative of AB0, negative of AB0 is, since AB0 is minus, so it's going to be negative, it's going to be plus. So plus, okay, then plus 2 EI upon L. What is negative of theta B0? It's minus, so I'm going to put minus 16 EI, okay, and fixed end moment at BA is equal to 2 EI upon L, and again minus of this is PL squared upon 16 EI plus 4 EI upon L minus PL squared upon 16 EI, and if you do this, you will get this 4 EI cancels, EI cancels, EI cancels, 4 goes into this 4 times, this goes into it 8 times. So if you look at this, L takes away this square, this L takes away this. So you have PL upon 4 minus PL upon 8, which is equal to PL upon 8. And if you look at fixed end moment BA, you will see that again EI cancels, L cancels this, 2 cancels this, this cancels this, EI cancel. So you have P upon 8 minus P upon 4. So it becomes minus PL upon 8. So therefore, what does that mean? Fixed end moment, positive PL upon 8 is, positive is anti-clockwise and minus is clockwise. So under this load, PL upon 8, PL upon 8. We've obtained this from first principles. Now I'm going to quickly go ahead and look at some other kind of loads so that you can convince yourself that all the fixed end moments that you have in handbooks Okay, you can compute using this method. Only thing, what are the steps in this method? I'm going to write down the steps. First, take the simply supported and obtain theta AB and theta BA due to the loading. Then 2, the fixed end moments, get fixed end moments. This is fixed end moments. This is my notation. Okay? So then get fixed end moments by substituting minus theta AB 0 and minus theta BA 0 into slope deflection equations. Okay, so let us just see. So let me again take this. Let me take this case. W kilonewton per meter, length L, EI. What are the fixed end moments? Well, take simply supported and take UDL with W. What's my bending moment diagram look like? My bending moment diagram is a parabola where this is equal to WL squared upon 8. So my curvature diagram is going to be M by EI diagram is going to be WL squared 8 upon EI. So therefore, how do I find out theta AB 0? Put a moment at this point. So this is sagging moment. This one, if I put, is hugging moment. And for this moment, apply a moment there. One, this is my M1, this is my M2, and therefore theta AB 0 is equal to area under this curve. What is it that equal to? It is equal to 2/3 WL squared upon 8 EI into L. That's the area under this curve. Where is its centroid? Centroid is in the center. So for this, it's going to be equal. So this is sagging, this is hugging. So centroid value will be minus half. That's going to be equal to, subtract, it's going to be WL cubed minus upon 24 EI. And similarly, when you do theta BA equal to 0, you will get plus WL squared upon 24 EI. So take the negative of these and substitute into the slope deflection equations, and what you get? Fixed end moment at AB is equal to 4 EI by L into negative of minus omega thing becomes WL squared upon 24 EI plus 2 EI upon L, and theta BA is plus, so negative of that is minus WL cubed upon 24 EI. If you look at this, this will become LL will make it WL squared, EI cancels, 6 is going to be minus WL cubed by this. So if you put it together, you will see that this turns out to be WL squared upon 8. Similarly, when you find out the fixed end moment at BA, you will find it is equal to WL squared by 8. What does that mean? That means that under this loading, FEM over here is going to be WL squared by 8, and this is going to be clockwise WL squared upon 8. Check, you will see that this is indeed what is given in the handbook. Let me finally do one more problem and convince you that I have not constructed this to make life complicated for you. It is just that any loading you can always find out, put that same loading, put it on the simply supported beam, find out the rotations of the two ends, and put the negative of the two rotations into the slope deflection equations, and you will get your fixed end moments. Okay? I am going to do a final one before I show you how this is going to get used. P, and this one I am going to say is applied at A and B from the right end, where the total length is L and EI. Okay? So in this case, again, I am now going to just go through the steps very quickly because we've already spent a lot of time on this. Okay? Note that if you draw this, you will see the bending moment diagram looks like this. So this is my bending moment diagram, and LAI is going to be equal to the M by EI diagram. Again, for theta AB, this is my virtual moment diagram, and for theta BA, this is my virtual moment diagram. And therefore, now these are two different, so let me find this out, the area under this curve. So area under this curve, and then I'll find area under this curve and add. So if you look at it, theta 1 into theta AB 0 is equal to, so the area under the left hand curve is going to be equal to PAB upon LEI multiplied by A by 2. This is the area under this curve multiplied by the at its centroid. What will be the centroid? The centroid, if you look at it, is going to be 2/3 A from this side. Okay? 2/3 A. Or conversely, I can say that it is equal to L minus 2 by 3A from this side. So what will be the value at this point? You will see that this is going to be equal to L minus A by 3. So I'm going to put that down. So it's going to be equal to L minus A, 2A by 3, the entire thing divided by L. And note that since this is hogging, this is going to be minus on the outside. And then the area under the other curve is going to be equal to, this is going to be B by 2. B by 2. So this is the area under this curve. And what is it at? At 2/3 B from this end. So the value of this is going to be equal to, again, minus outside 2/3 B upon L. Okay, because it's 1 at L, so this is going to be 2/3 B upon L. So this is theta AB. Let me put these things down properly. L upon L is 1. So it's going to be 1 minus 2A upon 3L. So I'm going to make this P A squared B upon 2EI, and inside is going to be equal to 1 minus 2A upon 3L and plus PAB squared L upon EI multiplied by minus 2b upon 3L. This is theta AB, and similarly you will see that theta BA is equal to just the same and just the opposite way. It's going to be PAB squared L upon EI. The only difference that you will have over here is that, over here, all of them are minus. So this is going to be minus and plus. I'm taking the minus inside. So this is going to be minus and plus. So this case, this is going to be positive, because both, if you look at it, both of them are sagging. Okay, so it's positive. So you'll have PAB squared into L upon EI, and on this side it's going to be 1 minus 2b upon 3L, and then you're going to have PA squared B upon LEI multiplied by 2A by 3L. Very complex equations, but simple to actually go through. Okay, so now I have to substitute the negative of these into the moment equation. So if I plug that in, what do I get? I'll just do it for MAB, and then MBA I can just put it at equal to. So the fixed end moment is equal to, if you plug it in, 4EI upon L into minus of theta AB. So it's going to be PAB squared upon 2EI, and minus here you will see is going to be equal to 1 minus 2A upon 3L plus PAB squared upon LEI, okay, into minus of that becomes plus, so this is going to be 2b upon 3L, and plus 2EI upon L of minus of that, so this is going to be PA squared B L upon EI into minus of 2A upon 3L. Okay, then I have plus P A B squared upon LEI, and that's going to be equal to 2B upon 3L minus 1. Okay. So now I'm going to substitute all of these in and write it out throughout explicitly, and then what I get is I'm going to take PAB outside. Okay, just for the sake of completeness, I'm going to take PAB outside. So I get PAB upon L. Note EI cancels out, so I'm not going to keep. So this is going to be AB upon L. So inside, what do I get? 4. Note that I've taken L squared outside, L and L outside. Okay, so I get just 4 into A. So I get 4A, and then minus 8A squared upon 3L, then plus, here I get 4 into 2B, so it's going to be plus 8, and then AB's got B comes out, so it's going to be 8B squared upon 3L. That I get from these two terms, and then I'm going to find out from these two terms. PAB I have taken out, so I have A here and 2. So this is going to be equal to minus 4 A squared upon 3L, 2 into 2, 4A, and on this side I'm going to get plus 2 into 2, 4, and then AB goes out, so it's B squared upon 3L, and then minus, let's see what I get over here, I get B, so 2B, so minus 2B. So here, if I take P upon L squared, you will see that this becomes 12A squared upon 3L. So what is that? That is equal to, so I'm going to write it down, 4A minus, okay, 4A squared upon L plus B squared. So what I get is, I get 4A squared L minus 4B squared L. Okay, that you'll see. Okay, minus minus, you get plus over here. That's what I've done. Minus 2B. Okay, now note that this becomes A plus B by L, okay, 4 times A, B plus L, and you can substitute all of those in, and ultimately you will see that this turns out to be, when you substitute, you will get P, put A and B, you will get that this is equal to P into A B squared by L squared, and this turns out to be P A squared B upon L squared. Now substitute, you want to check A equal to, put A and B L by 2, L by 2, and you will see, you will get that, you will get PL upon 8, PL upon 8, which is what you get earlier. Okay? So I'm going to stop over here